Hello again, folks. We're on to lesson 6 in our series of trig lessons for students studying A-level maths in year 12. And in this lesson we're going to look at deriving and using some trig identities. Okay, so let's start by deriving a couple of trig identities that we need to know in year 12. So here we've got a circle. You can see it's got a radius of r, and we've got a point defined on that circle, point P, which would have coordinates x and y. And so from there we can make that familiar right angled triangle with an angle theta. X and y are the adjacent and the opposite. And from there we know all the basic trig ratios. We know sine theta is y over r. We know cos theta is x over r, and tan theta is y over x. Let's do a little bit of work with these. First of all, from sine theta equals y over r, we could write that y equals r sine theta. And similarly, we could write x equals r cos theta from the cos theta ratio. Now, if you think about Pythagoras' theorem, it would say that square on the hypotenuse is equal to the sum of the squares on either two sides. So we could also write that x squared plus y squared equals r squared. We could get this formula by just considering the equation of a circle. Let's sub in our values for x and y. So now we've got r cos theta squared instead of x squared, and we've got r sine theta squared instead of y squared, and that would be equal to r squared. So this is going to give us r squared cos squared theta plus r squared sine squared theta equals r squared. And you'll notice that the r squareds all cancel out there. So we'd end up with cos squared theta plus sine squared theta equals 1. And that is our first trig identity. Sine squared plus cos squared equals 1. So you notice at the bottom I've written a triple bar on the equal sign. That means identically equal to. So it's telling us that this equation works for every single value of theta. Okay, let's look at our other trig identity that we want to derive. Again, let's take the same starting point. And again, we can write that y equals r sine theta, and that x equals r cos theta. Now if we take tan theta equals y over x, we could also write that as r sine theta over r cos theta. And again, the r's would cancel, so we get sine theta over cos theta. That works for almost every single value of theta. The only thing we've got to watch out for is we don't want cos theta equal to 0, because then we get a divide by 0 on the bottom of that fraction. So there's our second trig identity. Tan theta is identically equal to sine theta over cos theta. Right, well, let's see if we can use these then. Simplify the expressions. So let's start with the first one. Start with sine squared 3 theta plus cos squared 3 theta. Well, you could imagine we could sub in, say, I don't know, alpha equals 3 theta into both, and where we get sine squared alpha plus cos squared alpha. So we can say that this one is equal to 1, just using that first trig identity. That was easy. Let's look at B. Okay, let's start by factorising out that 5. We get 1 minus sine squared theta. Now let's have a think about that for a second. So just on the side, let's think. We know that sine squared theta plus cos squared theta is equal to 1. if we were to subtract sine squared from both sides, we'd get that cos squared theta equals 1 minus sine squared theta. Okay, so that tells us then we could take 1 minus sine squared theta and write cos squared theta. Okay, so we've got now that our initial question 5 minus 5 sine squared theta is actually equal to 5 cos squared theta. Okay, to turn our attention to part C, sine 2 theta over the square root of 1 minus sine squared 2 theta. Okay, so first of all, we can say we've got sine 2 theta over the square root of cos squared theta, just using that little trick from the previous question. Actually, that's 2 theta, isn't it? So then if we square root that, we would get sine 2 theta over cos 2 theta, and sine of a cos is tan, so that would be tan 2 theta. There we go. Okay, this one's a proof. Prove that cos to the power 4 theta minus sine to the power 4 theta all over cos squared theta is equal to 1 minus tan squared theta. All right, well, I remember having a bit of trouble with these kinds of questions back when I studied A-level maths, and the best advice I can give you is that you just got to build up a bit of experience and learn a few of the tricks. So persevere with these kinds of questions. Don't give up. Sometimes you try for a bit and scrap and start again, but if you persevere with it, it will come to you eventually. The best thing you can do is to think about what bits of maths can we apply in this kind of situation. Well, straight away I'm noticing that cos to the power 4 theta minus sine to the power 4 theta could be a bit tricky, but spotting the difference of two squares there, I don't know if you noticed that. So the difference of two squares, basically, a squared minus b squared is the same thing as a plus b times a minus b. So let's see if we can apply that in this situation. It's a proof, so we've got to start with the left-hand side, which is equal to cos to the power 4 theta minus sine to the power 4 theta all over cos squared theta. Let's apply that difference of two squares. So on the numerator, that would become cos squared theta plus sine squared theta times by cos squared theta minus sine squared theta. And that's all divided by cos squared theta, isn't it? Okay, so the first bracket there, cos squared theta plus sine squared theta, is actually just equal to 1, isn't it? So now we get cos squared theta minus sine squared theta all divided by cos squared theta. So we can split the numerator up into two fractions. We can say that the first one is cos squared theta over cos squared theta, and the second one is sine squared theta over cos squared theta. So cos squared theta over cos squared theta is just equal to 1, and sine squared over cos squared, well, sine over cos is tan, so sine squared over cos squared is tan squared. So now we've got minus tan squared theta, and that's exactly what we were looking for. So QED. All right, given cos theta equals negative 3/5 and theta is reflex, find the value of sine theta. Okay, this is going to take a little bit of thought. We'll start with our trig identity, sine squared plus cos squared equals 1. Okay, and because we know cos theta is minus 3/5, we could sub that in there, couldn't we? We could say that sine squared theta plus negative 3/5 squared is equal to 1. and quickly work that out. Sine squared theta plus 9 over 25 is equal to 1. So sine squared theta will be 1 minus 9 over 25, which is 16 over 25. So now if we square root both sides, we could say that sine theta is either going to be 4/5 or negative 4/5. And we need to figure out which one of those it is. This is where we turn to the familiar unit circle cast diagram. All students take care and have a little bit of a think about this. So it says that theta is reflex. Okay, so that means it's got to be somewhere in either quadrant 3 or quadrant 4. I'm not sure which at this stage. But it also says that cos theta is negative. Now, cos theta in quadrant 4 will be positive, so it tells us that this is the quadrant we're interested in, quadrant 3. That's where cos would be negative. So let's have a think. In that quadrant 3, sine would also be negative. So now we've figured out that sine theta must be minus 4/5. Okay. Given sine of beta is 2/5 and theta is obtuse, find the value of cos beta. Okay, so we start the same way. Sine squared beta plus cos squared beta is equal to 1. And we can put that in. That is 2/5 squared. So now we've got 4 over 25 plus cos squared beta equals 1. Cos squared beta must be 1 minus 4 over 25, which is 21 over 25. So cos beta is either going to be the square root of 21 over 5 or the negative square root of 21 over 5, and we've got to figure out which one that's going to be. So let's look at the cast diagram. Okay, so theta is obtuse. So that tells us then that we're looking at this quadrant number 2 in our diagram. In that quadrant, cos would be negative, so we can write that cos of beta is negative the square root of 21 all over 5. Let's have a look at another example. Given p equals 3 cos theta and q is 2 sine theta, show that 4p squared plus 9q squared equals 36. Okay, so if you're not sure where to start, just think of the two trig identities we've got. We know that sine squared plus cos squared equals 1, and we know that sine over cos is tan theta. Just looking at the fact that we've got squares in that expression, 4p squared plus 9q squared, makes me think probably we're going to use sine squared and cos squared as our trig identity here. So let's start with that and see if we get anywhere. It's always worth just having a bit of spirit of trial and error. Try something, see if it works, and if it doesn't, scrap it and try again with another plan. So here we go. Sine squared theta plus cos squared theta equals 1. So p equals 3 cos theta. We could write cos theta as p over 3 then, couldn't we? So this would be p over 3 squared. Q equals 2 sine theta. So sine theta is q over 2. So again, we could write that as q over 2 squared. Put those equal to 1. Okay, this is looking all right, actually. So we've got q squared over 4 plus p squared over 9 equals 1. We want to get rid of those fractions. We haven't got any fractions in our term over there. So let's multiply through by 36, which would give us 9q squared plus 4p p squared equals 36. And if we just rearrange that, 4p squared plus 9q squared equals 36 was what we were after. Nice. Okay, here's some questions for you to have a go at. And as ever, give those a go and get in touch if you've got any problems. Stay safe. Bye for now.